In these machine problems, we have 5 variables. We have FR, right, which is always basically going to be the object you're trying to move, either the force it resists with, its weight, whatever, and dr is going to be the distance that you move the object. Fe is going to be how much effort you have to apply using the machine, right? Hopefully the effort will be less than Fr. That means the machine is making the work easier, and you're going to apply your effort through some distance, dE. And then we also know how to define the efficiency of a machine, so another variable will be efficiency, right, which is a measure of how much of your input work actually becomes output work. So those are your 5 variables. And then we have a couple equations. We have an equation to calculate the mechanical advantage, Fr over Fe, and the ideal mechanical advantage, Ima, dE over dr. So those are 2 of the equations, and then the other one, the other 2 I guess, is efficiency, is work out over work in, times 100, right? But to work with the decimal, or to work with the percentage, you got to make it a decimal. So that's times 100. And then we also have efficiency is Ma over Ima times 100. And just be aware, right? The definition of work is force times displacement. So the work out is really Fr dr. So it's another way to think of this equation. And the work in is Fe dE. Okay. So sometimes that'll be useful to remember that equation. And that's it. So when you get these problems, identify what's what, and then go to your equation and figure out what you can solve for.
Yeah, can you say the top two again?
Say what they are?
Yeah.
Okay. This would be the resistance force, so that's either the weight of the object, right? Remember, when you're using a machine, you're trying to move something. It doesn't want to move, so it's resisting that. And then dr would be how far you actually move it. Fe is how much force you have to apply to move it. dE is how far you move your effort. And then efficiency is the equation.
So the Fr is higher than Fe, and the dr is less than the dE.
Yeah. That's the whole. That's when your work is easier. That's the case. Yeah.
You get dE.
dE is the distance that you move your effort force.
What should we say for efficiency? Just like
how much of the input work becomes output work. So if we look at this wheel and axle again, remember I'm lifting 9.8 newtons, right, a kilogram, and I'm pulling here. So what would the Fr be? 9.8, right? The effort is whatever little bit of force I apply here, right? And we saw it's not nearly 9.8, right? I could just hang 170 kilograms, and I'm able to move it. So my effort is much less than my Fr. My dE, my effort distance, is the distance my hand goes, and the dr is how far this actually moves, right, while I'm doing that. Okay. So those are your variables. After that, you would just use your equations to calculate whatever. All right, so in 79, you have a person raising a piano through a distance of 5 meters. So I'll just leave this here, and we'll use this to list our variables. So Takeshi raises a 1200 Newton piano. So what is that variable 1200? Fr, right? carries it through 5 meters. What is that? dr, 5 meters. He pulls 20 meters of rope. dE, right? So those are the variables we have. And then part A says how much effort force if the machine were ideal. Now, an ideal machine, the efficiency is 100% because there is no friction. So we actually have E as a variable. So now we want to figure out what is his effort force if the efficiency were 100%. So we want to go to this equation. So efficiency is work out over work in times 100. But we said another way of writing work out and work in is FRDR.
Why is E 100% again?
Because there's no friction. It's ideal machine, for part A. So now we could say 100 equals the FR, which is 1200, through 5 meters over the effort goes through 20 meters times 100. So bring your 100 over, you have 1 equals this, and then FE is 300 newtons. Right. So he will exert 300 newtons to move the 1200 newton piano. Part B says that what force is used to balance the friction force? So this is what his effort force would be if there were no friction, if it were ideal, but it's not. The actual effort is 340 newtons. So how much force does he have to use to overcome friction, basically? 40 newtons, right? So the answer to B is 40 newtons. So the extra force is used to overcome friction. What is the output work? So now that's FRDR, right? We wrote that here, FRDR. So work out is the resistance force and the resistance distance. So that's 1200 times 5, or 6,000 joules. What is the actual input work? So that's WI is FEDE. So that's actually, let's see, he's actually using 340, so we'll use that. And it's moving through 20 meters. So that's 6,800 joules. And then E asks for the mechanical advantage, so we have our equation for that. FR over FE. So 1200 over 340. And remember, these are newtons and newtons, so the units cancel, and it's just a ratio, 3.5. So it's basically his force is multiplied by 3.5 times is what that's telling us. For 24, it's based on example problem 4, so let's walk through example 4 so we understand it, and then I'll just explain what you would have to do the next one. So in 24 is based on example problem 4. So let's see here. It tells us that, let's look at the rear wheel of the bicycle. So here's the bicycle rear wheel. Okay, and you know on the rear wheel you have all your gears. So that represents one of the gears. And you know that to that is attached a chain, right? So you're over here and you're pedaling over here, that's pulling the chain. The chain is pulling on the gears, and then the wheel's turning, and that's how we go down the road. All right. It tells us in this problem that the wheel has a radius of 0.356 meters. So actual wheel is 0.356 meters. That's not your effort, that's your resistance, right? Because your effort is here is being applied by the chain. So the effort force is actually this. The resistance force would be the pushing on the road. So this is actually the radius of the resistance, is the wheel. It tells us that the gear has a radius of 4. So that's this here, this little bit here, from here to here, is the radius of the effort. That's 0.04 meters. Tells us that we're going to pull the chain with 155 newtons, so that's your effort force, 155. And the rim of the wheel then moves 14 centimeters. So when we do that, this thing will rotate through a resistance distance of 0.14 meters. So we pull here, we rotate, this will move 0.14 meters, and the efficiency is 95%. So part A says, what is the IMA? So for a wheel and axle, which is what this is, only in this case, the force is applied to the axle in order to move the wheel. Our example there, we applied to the wheel to move the axle. So A, the IMA for wheel and axle is, IMA is always dE over dr, but if you wrote down your equations yesterday, then it's the radius of the effort over the radius of the resistance. So that's going to be, the effort radius is 0.04, and the radius resistance is 0.356. So that's how they get 0.112 there. So that's not what this here, because for 24 we're going to change the effort radius. For B, it says solve for the MA. So efficiency is also MA over IMA. So you need to figure out, what do I have that's going to get you to the MA? Okay, and you have efficiency and you have IMA, so you can actually use this equation. So I'm just going to convert this to a decimal straight away. So 0.95 equals MA over 0.112. So the MA is 0.106. It's always going to be lower than the IMA because of friction. C, solve for the effort or resistance force. So how much force is actually being applied down here, right? The resistance force actually be longer on the road. So how much force are you applying to the road by doing this? So C, the resistance force, you now have your mechanical advantage, and you know FR and FE. So 0.106 equals FR over the effort 155. So that is 16.4 newtons. So notice you're applying 155 newtons to apply 16.4 newtons to the road. So actually I was wrong. This arrow would be much smaller than that one. And then D, how far was the chain pulled to move 14 centimeters? So now let's go back to, we have the IMA, and we know we know RE. So we need to know how far does this go. Is that what we want? It told us, what did it say? We pulled the chain, 14. Okay, so IMA is dE over dr. So how far was the chain pulled? We know IMA is 0.112. The resistance side moved 0.14 meters. So how much did the chain move? That's dE. So dE was 0.14 24, all that it said happened was that we changed the gear radius. We doubled it. So if you double it, it's right. So you're on the road. You switch your gears on your handlebars. The chain jumps up to the next biggest gear. So now instead of RE being 0.04, RE is 0.08. Right. So now you want to work through again same way. So instead of 0.04, you make this 0.08, and you get 0.225. Okay. Then you do this here. Instead of 0.112 here, you put 0.225, and your MA becomes 0.214. Then here, this is 0.214. Amount of force is still the same, so the output force is now 33.2. And here, you want to put 0.225. Still 14, so the effort is 0.0315. So that's all.